Greetings, and welcome to the next exciting installment of Digital Design. Our topic today is logic gates. So logic gates are circuit elements that take zeros and ones in and put zeros and ones out. And they can do all different functions that we'll talk about. Simplest logic gates just take a single input and generate a single output. One of our favorites is the NOT gate. The NOT gate has an input called A, an output called Y, and the symbol is a triangle with a circle, and the circle is indicating inversion to do the opposite. The Boolean equation is Y equals A bar, usually pronounced Y equals not A, and the NOT gate does the opposite of the input. So if we put in a 0, we get out a 1. If we put in a 1, we get out a 0. This is kind of like what my son did when he was 2 years old. Does exactly the opposite of what you ask him. The other single input logic gate is called a buffer, and the output just follows the input. If we put in a 0, we get out a 0. If we put in a 1, we get out a 1. So the Boolean equation of Y equals A. From a logic point of view, this seems useless, but sometimes from an electrical point of view, buffers could be helpful. For instance, they might put out the same output but at a different voltage level, or they might put out the same output but with greater power to drive something like a motor or a light. So single input logic gates aren't all that exciting. With two inputs, we get a little bit more interesting. The most common two input gates are AND and OR. An AND gate produces a true output only when both inputs are true. So the inputs are A and B, the output is Y, and the Boolean equation is called Y equals A and B, written just like multiplication. The truth table here, we can do 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. So the output is only true when both inputs are true. The OR gate is true if either or both inputs are true. So 0 or 0 makes 0, 0 or 1 makes 1, 1 or 0 makes 1, 1 or 1 makes 1. The symbol for OR is curved, and the Boolean equation is Y equals A or B. So AND looks like multiplication, and sure enough, the truth table does look like A times B. Or the symbol can be addition, but this is not quite addition because 1 or 1 makes 1. Sometimes mathematicians use the symbol intersect, A intersect B for AND, A union B for OR, but there's no intersect or union keys on the keyboard, so I prefer to stick with the regular Boolean equations. There's some more two-input logic gates. An exclusive OR gate produces an output that's true when one or the other input, but not both are true. So 0 XOR 0 makes 0, 0 XOR 1 makes 1, 1 XOR 0 makes 1, 1 XOR 1 makes 0. The output is true when either of the inputs are true, but not both. The symbol is like an OR, but with two lines on the input, and the Boolean equation is written A XOR B, a plus with a circle around it. A NAND gate is like an AND, but it has a bubble on the output, so it does the opposite. The Boolean equation is Y equals A and B bar, and it's the opposite of AND. So AND was 0, 0, 0, 1. NAND would be 1, 1, 1, 0. Not of AND. 0 NAND 0 makes 1, 0 NAND 1 makes 1, 1 NAND 0 makes 1, 1 NAND 1 makes 0. A NOR is the opposite of an OR. It's like an OR gate with a bubble. The Boolean equation has the bar over it, and so the opposite of OR is 1, 0, 0, 0. Exclusive NOR is the opposite of XOR. Again, the symbol has the bubble on the output, the equation has the bar over it, and it's the opposite of this table, so 1, 0, 0, 1. We could consider multiple input gates. So for instance, a 3-input NOR is true, well, 3-input OR would be true when any of the inputs are true. So a 3-input NOR would be true when none of the inputs are true. That's this row. So Y is true when the inputs are all zeros, otherwise it's false. A 3-input AND would be true when all of the inputs are true. It's only true when all inputs are true. Exclusive OR for multiple inputs is kind of strange. At first glance, you might think a multi-input XOR would be only true when exactly one of the inputs is true, and that's not the case. Instead, we define multi-input XOR as odd parity, when an odd number of inputs are true. So for example, a 3-input exclusive OR would be true when one of the inputs is true or all 3 of the inputs are true. Drawing schematics is very helpful, but it's hard to do on a keyboard. So we often want to describe our gates with text instead. And we'll be using a hardware description language in this class called System Verilog. This is an industry standard, very widely used language for describing hardware. And here's some first examples. So let's say we wanted to define some logic gates. We've got inputs A, B, and C, and 5 outputs from 5 different gates. We could have a NOT gate, an AND gate, an OR gate, a NAND, and an XOR. Each gate has a name, just to tell them apart. This NOT gate could be named Bob, but instead we're just going to name him G1. And then the signals are listed as output, and then the inputs. So this NOT gate has input A, output Y1, and the NOT gate just happens to be named G1. Then we have an AND gate named G2 that has input A and B and produces Y2. We have an OR gate that takes inputs A, B, and C and produces Y3 and so forth. So this is a textual description of the circuit. The operations of AND, OR, and NOT date back to a British mathematician named George Boole. He lived in the first half of the 19th century. Boole was born to working-class parents who couldn't afford to send him to school, but remarkably he taught himself mathematics by himself sufficiently well that he was able to get a faculty position at Queen's College in Ireland. So quite a character. Boole wrote a treatise called An Investigation into the Laws of Thought, and he felt that the way the mind worked was that we considered propositions that were either true or false, and we could combine these propositions in a way to get to conclusions. So in hindsight, maybe the way human mind works is not quite as rational as Boole suggested, but he laid the foundation for binary variables and truth and falsity. And he introduced the 3 fundamental logic operations, AND, OR, and NOT.